Children, I hope you have gone through my previous video, and today we will continue further. Today in the chapter Coordination Compounds, we will study about Werner's theory of coordination compounds. Let's begin with the postulates of the theory. Now, according to this theory, there are two types of valencies shown by the central metal or ion in a compound. First is primary valency and the second is secondary valency. Now, primary valency is the ionizable valency, whereas secondary valency is non-ionizable. Primary valency corresponds to the oxidation number, while secondary valency corresponds to coordination number. For example, in a compound CONH3 6Cl3, this is the compound CONH3 6Cl3. Now, in this compound, the primary valency is 3 because ionizable part is Cl3. Okay, and the secondary valency is 6 because the non-ionizable part is 6. Alright, NH3 are 6. They are within the brackets. Within this bracket means that it is non-ionizable. Outside the bracket means it is ionizable. So cobalt is attached to 6 ammonia molecules, so it is having secondary valency 6 and 3 chloride atoms, so it is having primary valency plus 3. Now primary valency is satisfied by negative ions, that is anions, while secondary valency is satisfied by ligands. Ligands can be neutral, negative or positive also in rare cases. Now every metal has a fixed number of secondary valencies. That is, it has a fixed coordination number. Coordination number, you know, the neighboring atoms which are present. Now the secondary valency are directional and they are responsible for the definite geometry and isomerism of coordination compound. Primary valency in the complex is shown by dotted lines. See here, shown by dotted lines. Secondary valencies, they are shown by dark lines. In all cases, metal or metal ion should satisfy both primary valency and secondary valency. Now, structures of coordination compound on the basis of Werner's theory. Now, if a coordination compound has a formula COCl3.6NH3, then the structure will be, because there are 6 ligands which are showing secondary valency, so 6 like this, and 3 ionizable chloride atoms. So here, it will be written as CONH3 6 within the brackets and Cl3 outside, because Cl3 is the ionizable part. Okay. Similarly, if the compound is CONH3 5 Cl3, so in that case the compound will become CONH3 5 Cl2. Secondary valency is 6. So 1 ammonia has been removed, so in its place 1 chlorine will get transformed into secondary valency, and only 2 will be primary valency. 2 will be shown by dotted line outside. Only 2 will be able to ionize. Similarly, if it is CONH3 4 Cl3, in that case 2 chlorine atoms will come inside the coordination sphere. See, converted into dark lines. Only 1 chlorine will be ionizable, shown through dotted line. If it is CONH3 thrice Cl3, then all the 3 chloride will come inside. There will be no ionizable part to it. Alright. Now let us come next to the rules for writing coordination compound. There are a number of rules for writing the coordination compounds. First rule is that the formula of cation, whether simple or complex, is written first, followed by that of anion. The coordination entity is written in square brackets. these big brackets over here, this one and this one. Then within the coordination entity, symbol of central metal atom is written first. First you write the metal atom symbol, followed by ligands in alphabetical order. Okay, if there are more than one ligands, it has to be in alphabetical order according to following rules. First rule is different ligands are arranged alphabetically according to the first symbol of their formula. Now for example, H2O, NH3, NO3, etc. The first symbol is H, N, NO, like this. Now in the ligands having same defining atom, the ligand with fewer such atoms is cited first, followed by more atoms like NH3 and N2. Both have got N. So NH3 will be written first and then N2, because in NH3 there is a single N. Alright. Now if defining atoms are same, symbol decides the sequence. For example, NH2 minus and NO2 minus. Defining atoms are the same, but symbol will divide. So NH2 minus will come first and NO2 minus will come later on. Polydentate ligands are written alphabetically. Now in case of abbreviated ligands, if it is written in short form, the first letter determines its alphabetical position. Polyatomic ligands, they are enclosed in parentheses, that is brackets, without any separation inside the square bracket. There should not be any space between the representation of ionic species within the formula. The abbreviations for certain ligands like PY for pyridine, EN for ethane, 1,2-diamine should be enclosed in parentheses. The number of cations or anions to be written in the formula is calculated on the basis that total positive charge must be equal to total negative charge. When the formula or coordination entity is written without any counter ion, the charge may be indicated outside the square bracket as a right subscript with the number before the sign. For example, like Ni NH3 whole 6, bracket will close, and on top you can write 2 plus. Some common examples are COCl2 NH3 whole 4 Br. Now see, in this Cl is cited first and then NH3. Why? Because alphabetically C comes before N. Then Cr H2O whole twice NH3 whole 4 Cl2. Here H is written before N. Ru NH3 whole 5 N2 NO3 whole twice. So NH3 precedes N. Alright. So this way it has to be done. Nomenclature of coordination compounds. Now in this, first is order of naming ions. In ionic complex, the positive ion, that is the cation, is named first, followed by the anion. Name is started with a small letter, like for example K3FeCN6. It is named as potassium hexacyanoferrate within brackets in Romans 3. For non-ionic complexes or neutral complexes, CONH3 whole 3 Cl3, the name of the complex is written in one word: triamine trichloro chlorido cobalt. Triamine trichlorido cobalt, and within brackets in Roman figures you will write 3. Okay. Then second is naming the coordination entity. In naming the coordination entity, number and names of ligands are written first, followed by the name of the central metal atom. The oxidation number of central metal atom is expressed by Roman numerical. Metal atom as well as ligands are written without any space between them. When you are naming the ligand, anionic ligand always ends with O in general. If the name of an ionic ligand ends in IDE, ITE or ATE, the final E is replaced by O. So IDE becomes IDO, IDO, ITO, ATO, etc. Like take for example, Cl minus will be written as chlorido. NH2 minus will be written as, it is amine na, it will be written as amido. O2 minus oxo. O2 2 minus will be written as peroxo. Peroxide will be written as peroxo. Sulfate will be written as sulfato. Okay. And HS minus will be written as mercapto. For positive ligands, they end with IUM. Like NO plus, it will be written as nitrosonium. NH2, NH3 plus hydrazinium. NO2 plus nitronium. Then you come to neutral ligands. Neutral ligands, they are named as such, like NH2, CH2, CH2, NH2. It is ethylene diamine or ethane 1,2-diamine. C6H5N, pyridine. C6H5 whole thrice P, triphenyl phosphine. PH3, phosphine. So this is how the neutral ligands are named. Next we come to order of naming ligands. According to latest IUPAC recommendation, name of ligand surrounding the central metal are written in alphabetical order of preference irrespective of their type. The prefix di, tri, tetra, etc. are not considered while determining the alphabetical order. But for writing the formula of complex, ligands are placed in alphabetical order followed by name of metal, atom or ion. Numerical prefixes to indicate number of ligands in order to specify number of each kind of simple ligands. Greek prefixes di, tri, tetra, etc. are used. When the name of ligand itself includes a number such as ethylene, diamine, in such case you will not use di word again, you will instead use bis, bis, bi, so bis. For tri it will become tris, tetrakis, etc. for 2, 3 or 4 molecules, followed by the name of ligand in parenthesis. For example, suppose it is COEN whole thrice Cl3. It will be called tris-ethylene diamine, cobalt 3 chloride. Okay. When monodentate ligands like methylene, amine, triphenyl phosphine, etc. are repeated, the word bis is used instead of di. Next is naming of central metal ion. Name of negatively charged complex ion ends with 8 ATE followed by oxidation number in brackets. For example, K2ZnOH4 is called potassium tetrahydroxozincate within brackets 2. Oxidation number is 2, so in Roman 2. For cationic and neutral complexes, name of metal is written without any characteristic ending. For example, CONH3 whole 6 Cl3 is called hexaamine cobalt within brackets 3 chloride. So it is just as such. Next is oxidation state of central metal ion. Oxidation state of central metal ion is designated by Roman numeral in brackets at the end of the name of the complex without a gap between the two. Zero oxidation state is also shown within brackets. You have to write 0. Point of attachment: when a ligand can coordinate through more than one atom, then the point of attachment of ligand is indicated by putting the symbol of atom through which coordination occurs after the name of the ligand. For example, see here, in NO2, point of attachment is N, so you will write nitrito -N. In ONO, point of attachment is O, so you will write nitrito O. SCN, you will write thiocyanato S. NCS, thiocyanato N. So like this you will show through which atom, because there are more than, it can attach with through sulfur also, it can attach through nitrogen also. So you have to mention the point of attachment is with through sulfur or nitrogen. So you have to mention over here the atom through its symbol. A nomenclature of complexes containing complex cationic and anionic species. Coordination compounds containing complex cations and anions. They are named by writing the name of complex cation followed by name of complex anion. Example, see here, CrNH3 COCN6. It is called hexaamine because there are 6 ammonium. So hexaamine, chromium oxidation status 3. Hexacyanocobaltate, again oxidation status 3. So you have first written the name of complex cation followed by the name of complex anion, and because anion, so ATE. Similarly here, PTNH3 PTCl4, it becomes tetraamine platinum within brackets 2, tetrachloridoplatinate within brackets 2. Okay, so this is how the nomenclature is done. I'll be in the study material that I'll be sending to you, I will give you the names of some common ligands and their formulas and their charge and the name given to the complex, a list of these, as well as some examples of how to name a few coordinate compounds. So you can go through them, try naming the compounds in your chapter. Number of questions are given for either naming the compound or from the formula give the name of the compound, or it can be from the name give the formula of the compound. Both ways the question can be asked in the exam. So practice it as much as you can. Just remember to follow the rules which have been told to you. Okay, and the remaining we'll do in the next video.